This demonstration is entitled Transforming an Information System into a Knowledge System. Now today we live in an information system era. Information systems are limited in the kinds of questions you can ask in them. And what we will demonstrate is the ability to take an information system and morph it into something called a knowledge system through the use of ontologies. And this will enable the ability to ask really powerful kinds of questions that would be very difficult to ask if you only had an information system. In this presentation, we will demonstrate how to transform an information system into a knowledge system, enabling the ability to ask very powerful questions that would be difficult to answer in an information system by itself. So the example we're going to use is one in healthcare. So in the upper left here we have a PowerPoint slide, and in this PowerPoint slide we see a table here in an electronic healthcare record system. In this table we see a column of patients and a column of clinical facts. These clinical facts contain diagnoses about a particular patient. On top of this we see something called an ontology used to classify the information here we see in this underlying table here. So what we're going to do is imagine that we've implemented this ontology in this thing called a soft schema here. And through the use of this soft schema, we will demonstrate the ability to ask very powerful questions. So say, for example, we want to find all patients here that have a diagnosis of diabetes here. Now we see in this ontology here, we see a node here called diabetes, and we have specializations of this general concept of diabetes. We have something called type 1 diabetes, something called type 2 diabetes, and underneath type 1 diabetes we have a specialization called brittle diabetes here. So let's see how we use a soft schema to answer this high-level question, find all patients here that have a diagnosis of diabetes. So we're going to show a select statement here, and it uses this thing called object-TC, which is the transitive closure of this particular graph here. And we're going to play computer here to show how this select statement is actually executed here. So what happens in this select statement here is we're looking for the parent in the transitive closure table of a node called diabetes here. And what we're going to do is find all descendants of diabetes here. And then we're going to do a join to the electronic healthcare record table here to find all of the clinical facts that correspond to descendants of diabetes here. And then what we want to do is return the names of the particular patients here. So we see that here. Now the thing to point out here is that the only thing we had to specify here is this high-level notion of this thing called diabetes. If we wanted to do this using simply the information system, we would have had to do a select statement with a hard-coded, comma-separated list of the different kinds of diabetes. That's fine and well, except for the fact that maybe tomorrow in the healthcare industry a new kind of diabetes is introduced. Any kind of application that you wrote in an information system with a hard-coded, comma-separated list will become incorrect. And so this PowerPoint slide here demonstrates the power of being able to take information and classify it into higher level categories. Rather than SQL code, let's look at an application that encapsulates this powerful capability here. And in this application, we're going to utilize a database that uses a soft schema to represent all of the data. So a soft schema consists of 6 relational database tables, and we're going to use that to represent information in an information system, and we'll use those same 6 tables to represent a knowledge layer used to classify the underlying information system. Let's look at examples of some of the data stored in our database here. Now TC-SQL features the ability to import XML documents. So what I'm going to show you here are a variety of XML documents that have been imported into our soft schema. The first XML document we see here is with respect to clinical trials. It is the result of doing a query on clinicaltrials.gov and downloading the results onto our machine here and then importing the XML into our soft schema here. And so this contains a variety of clinical trials. The next document we see is with respect to quality measures here. This is a NQF quality measure. Again, it's an XML document. The next XML document is a CCD document, so it's XML pertaining to healthcare information pertaining to a particular patient. And the next XML document is an XML document that's returned as a result of executing a natural language processing tool called MetaMap. And so we've imported all of these kinds of data into our system here. So let's take a look at our application here called Vocabulary Profiler. And let me start out by explaining some of the terminology we see here. The notion of a vocabulary in a soft schema vernacular means a collection of object graphs. The notion of namespace in the soft schema vernacular means a collection of class graphs here. Now, if we go back to our PowerPoint slide here where we were showing this flat table here, you can think of this flat table as a degenerate graph, where each record can be considered an object node, but there is no semantic relationships between the object nodes here. So now, going back here, if we look at our list of vocabularies here, what you see here are the XML documents I pointed out to briefly a minute ago. You also see other kinds of data. You see what are called ontologies here, SNOMED, for example, and ICD 9, 10. These are ontologies similar to what you saw in the PowerPoint slide here. And so you can think of the vocabularies collectively as a large collection of objects. And what this application called Vocabulary Profiler does is it provides a way of taking all your set of objects and categorizing them in various ways here. So for example, we're going to categorize all of the underlying objects with respect to a categorizer called SNOMED, which is an ontology here. So let's take a closer look at SNOMED here. SNOMED is a healthcare ontology consisting of approximately 400,000 healthcare vocabulary terms. Pretty much every kind of healthcare term you can imagine, and the semantic relationships between the various terms here. So now let's look at our application here, and what we're going to do is take all of our objects in our database here, and we are going to categorize them, classify them according to SNOMED. So let's go ahead and execute this here. And what is returned is a bar graph here. And if you look at the various bars here, you see body structure, clinical findings. These correspond to the immediate children here from our current node, which happens to be the root of SNOMED here. And what you see is a count of the number of objects in our database that are classified as clinical findings and body structure and all these other SNOMED kinds of nodes here. The way to think of this is the following. Let's go back looking at all of the children of SNOMED here. We see something called clinical findings here. Now, clinical findings is further broken down into subcategories here, and you could further drill down further and further here. And so there are many descendants here of clinical findings. So when we see the bar here that says 180, what that means is there are 180 objects in our database that correspond to one or more descendants of clinical findings. One of the things we can do in this application is click on one of the bars and drill down. So let's drill down on clinical findings here. And we see the following here. If we go up here now and look at all of the children of clinical findings, you'll see that the children of clinical findings correspond to the bars we see here now. Now, one of the things you'll notice here, if you were to add up all of these numbers here, they total more than the 180 that we saw in the total of the parent. And the reason why is because SNOMED is not a hierarchy, it's a polyhierarchy, meaning that a node potentially can have multiple parents here. We're currently looking at the SNOMED node clinical findings here. And one of the things you can do in this application is you can look at the details that comprise all of the bars you see here. So let's scroll up here. And again, here's our current node we're looking at, clinical findings. We can look at the details here. So we click on the Show Details button here, and we get a report that shows the following. We have a number of columns here. The ID and name column are the names of the objects in our database that correspond to descendants of the clinical findings node of SNOMED. And the descendants information of clinical findings is shown on the right here. So if we just scroll here real quickly, we see lots of different objects in different vocabularies here. So let's scroll down here a little further. For example, here we see an NQF object here. So this particular object is a member of this vocabulary, NQF. One of the things we can do here is let's take a closer look at the context of this particular object. Now I mentioned that all objects participate in a graph structure. So let's look at the ascendance of this particular object. So I'm going to click on this ID here and cut it out, and then I'm going to go to a SQL Server Query Analyzer window and paste in that value here, and let's take a look at its context here. And so here's our object here, acute infarction. We see it has as the parent NQF0246. So this is the particular quality measure that it participates in, and NQF0246 is part of NQF measures in general, and you see collectively that these three NQF vocabulary objects are part of a larger vocabulary called E-measures. So let's escape from here a second. Let's go back to where we were before. So you get an idea here that through this application we are able to classify lower level information, namely all of the objects in our database. Let's take a closer look under the hood to find out how this magical categorization is achieved. So to do that, let's go back to our PowerPoint slide here, and we see this ontology here. This is a generic ontology. Imagine this being something like SNOMED. In healthcare ontologies, what you'll find with all nodes is the following. You'll have the notion of a concept here, which is typically a character string, such as diabetes, and you'll have the notion of a code associated with this concept. So if this were SNOMED, you would have a concept called diabetes and a SNOMED code, say 1234. SNOMED is part of a larger collection of ontologies called UMLS. There are other ontologies which also may have similar kinds of concepts. So you may find the concept of diabetes, for example, in ICD-10. And in that vocabulary / ontology, it may have an ICD-10 code value of, say, ABCD. Now, what UMLS has done is to overlay their entire set of ontologies, 150 plus ontologies, with a superclass layer. And so they've introduced a second kind of code, something called a CUI, which stands for Concept Universal Identifier. So you may have the notion of diabetes in SNOMED and that same concept of diabetes in ICD-10. And in both vocabularies, they would have the same CUI value. So knowing this information, let's now go back to our detailed results we saw a minute ago here, and let's scroll down to the bottom here. And at the very bottom here, you see a reference to a vocabulary called sample CCD document. This is an XML document pertaining to clinical data for a particular patient here. And underneath here, you see references to, if you count these up, 23 different SNOMED codes. Let's examine how this vocabulary profiler tool was able to find these SNOMED codes in the first place. So let's do the following. Let's go back to our documents here, and I happen to have this particular document. And it's a bunch of XML code. If we look in here, we'll see an element here called code. with an attribute called code here and another attribute called code system here. So these two pieces of information are used in the query that allow you to find all of the objects in a database that have a SNOMED code descendant of clinical findings here. So that's how that works. Let's look at another XML document here. So this is a healthcare XML document for a particular individual, a CCD document. Let's bring another document into question here. This is another healthcare document. It's an RX document for an individual again. But I should point out something important here. In this first CCD document, we saw an element called code used and an attribute called code used, an attribute called code system used. Over in this other document, though, the notion of a code and a coding system is quite different here. What we see here, if we look closely here, is we have a tag here that says data types qualifier with a value of SNOMED here. And another element here of data types code with a particular SNOMED code here. So in both cases, they are both representing SNOMED codes, but they are representing them quite differently. So one of the magical things here that happens with this vocabulary profiler tool is in its design, it does not have a query that has hard-coded knowledge as to the names of the elements and attributes. Instead, it uses something called polymorphism. So both of these elements and attributes point to a higher level class concept here. So let's show this here in a query here. Okay, what the vocabulary profiler tool is doing is it's executing the following query here. It's saying, given this high-level class concept of vocabulary code system, find all of the particular instances here. And when we execute this, we see something called code system and something called qualifier. And in fact, they point to the particular instances that are used in these two documents here. So what this means is the following. Let's assume I want to integrate an entirely new kind of healthcare XML document into the mix here, and I want to be able to use it within the vocabulary profiler. What I need to do is a simple matter of inserting a couple new class connection records that will point to whatever structure is used to indicate a code and a code system kind of element. I need to insert a class connection record that points to this superclass called vocabulary code system. In that way, I never have to change the underlying code of vocabulary profiler. Now, what happens if we have an XML document that has no references to healthcare vocabulary code systems at all? What do we do in that case? Let's take a look at an example of that. So here we have our clinical trials document that we saw earlier. And I should point out here, if you were to scroll through this, you will find no references to any ontology coding systems or any ontology codes. So what is done in this case is the following. If you look at the elements here, we see a section of conditions here and a list of one or more conditions, and these reflect the kind of clinical conditions that must be met in order for a potential patient to qualify for the given clinical trial here. So what we've done here is applied natural language processing to these text strings here. And we're executing a tool called MetaMap, which is owned by UMLS. And what it does is the following. You pass in a string such as ulcerative colitis, and what it returns is a set of vocabularies and corresponding vocabulary codes that meet this, this definition here. It also returns these CUI values that I talked about earlier. So in the example I gave before of diabetes having a CUI value 5, 6, 7, 8, you would see that return from natural language processing. And I've described previously that TC-SQL has the ability to execute and import the results of natural language processing. So what happens is the natural language processing that is executed and the corresponding XML returned, that particular object graph is attached to the corresponding object graph you see here, and that graph is attached as a child of the given condition you see here. So in summary, what I've demonstrated here is the ability for this tool called Vocabulary Profiler, its ability to read in any kind of XML document and be able to run a query regarding healthcare questions. Even if the underlying XML has no knowledge of healthcare information at all, we've demonstrated how to morph it into something containing healthcare data. Let's look at another example. Let's choose a different categorizer. In this one, let's look at something called e-measures. So let's select that here. An e-measure is something called a quality measure. It's a way of asking how are we doing kinds of questions with respect to healthcare. So let's execute that. And we see underneath e-measures, two kinds of e-measures, AHRQ measures and NQF measures. Let's drill down into NQF measures. And we see a variety of specific NQF measures here. Let's scroll all the way down to the bottom here. And we see one called NQF 0528. The reason why I chose that one is because I happen to have the XML document corresponding to that particular quality measure. And this particular document answers the how are we doing kind of question, prophylactic antibiotic selection for surgical patients, NQF 0528. If we scroll through this XML document, it's very long and very detailed. And if we scroll down to the bottom, we find almost 16,000 lines of XML comprising this definition here. Now, let's look at a human readable form of this XML here. So I happen to have a web page pointing to that here. And what we see in a quality measure, in all quality measures, they have the following characteristics. There's the notion of a population, there's a notion of a numerator and denominator, and in these numerator and denominator specifications, we see various healthcare conditions that must be met here. If we scroll down to the bottom here, we see references to concepts in various ontologies here. So here we have a reference to ICD-9 concepts, ICD-10 concepts, SNOMED concepts here. So what you should take away from all of this is that if we go back to our vocabulary profiler here for a second, these particular NQF measures reference a number of concepts in other ontologies here. So let's drill down into NQF 0528. We see some subcategories here. Let's look at the details associated with NQF 0528. The details in this case will be the ontology codes that are used. And so we see the following here. In looking at the details for NQF 0528, we see the following. Over on the right here, we see a number of ICD-9 concepts. We see codes associated with those concepts. So we have a long list of ICD-9 codes. And to the left of that, we see the objects in our database that utilize these same ICD-9 concepts here. Interestingly enough, so what we see here are AHRQ vocabulary objects that happen to use the same NQF 0528 concepts. In conclusion, let me point out something very important here. Let me go back to the specification for this particular quality measure here. And again, I'll mention that this is very complicated here. It's very formal, but it's very complicated and long. Imagine if you could do the following. Imagine if you could take the XML form of this specification and push a button to compile it into running code, executable code. That would be an example of something I would call the holy grail, the ability to take a high-level specification of structured data and compile it into something that can be executed. What I've demonstrated here is the ability to provide steps leading to that general capability.